LAZR-X. So this is really the next generation of photoacoustic imaging system, where we've taken you know, all of the advantages of photoacoustic imaging and put them on the 3100 platform, acquisition platform. We have some new things on here as well. And I really want to stress that we're talking about co-registered multimodal imaging because we're collecting ultrasound, because we're doing things like Doppler imaging, ultrasound contrast, nonlinear contrast imaging, photoacoustic imaging, and the different submodes in photoacoustics, which I'll talk a little bit about. It's really a multimodal imaging platform. You get a lot of different information using this one platform. Things like blood flow, blood volume, blood oxygen saturation, anatomy, volumes, that kind of thing. So it really, I do want to stress, it is really multimodal. We have the advantage now of the touchscreen interface on the 3100 for enhanced workflow. We do have, you'll notice a new laser, for those of you familiar with our old system, you'll notice a new laser there, and I'll talk about that as well. And then we've got more flexible application-specific light delivery, and I have a fairly detailed slide about that to describe it. I'm pretty excited about it. And then some hardware and software tools for various applications. So first, for enhanced workflow, and those of you who already have and are using a 3100 will recognize this touchscreen interface. So that's the not the screen up there with the image on it up here. This is the clinical display where you see your image, and down here that's the touchscreen. So that's a new control panel, and it's completely customizable. So we can drag and drop different buttons here, different functions we use more often for certain applications, we can make more prominent on the panel. So because it's touchscreen, that really opens it up for making it quite customizable. And now we have PA mode on it over here. In addition to, of course, B mode, M mode, color Doppler, power Doppler, etc. We've got PA mode in here. And then we have all the sub-modes here, what we call the sub-modes. So you can image just using a single wavelength. You can image using the spectro feature to sweep across the entire wavelength range. We have the oxyhemo. With one click, you get oxygen saturation information. And the multi-wavelength imaging, which I'll talk a little bit about for doing especially things like spectral unmixing. So right here we're just showing the single wavelength imaging panel, and some of the advantages here of not having a keyboard and having a touch screen is that you can have sliders. So you see all the submodes there, you can have sliders, so we can just slide this up and down to change the wavelength. We can also bookmark wavelengths here, so it's a lot more user-friendly. When we get into multi-wavelength scanning, so this is again just clicking the multi-wavelength button, we can scan various components. So we can actually just choose what components we want to scan for. For example, oxy and deoxyhemoglobin if we're imaging something in vivo. If we're using some kind of photoacoustic contrast agent, like an optical dye or a nanoparticle, we can then add that component in as well. And the system will automatically select wavelengths that are appropriate for unmixing those components. We can also just scan our own wavelengths for those of you who are familiar with photoacoustic imaging, who know the wavelengths you want to visualize. This panel really gives you a lot of flexibility around adding wavelengths, taking wavelengths away, sliding them back and forth. So it's very, very smooth workflow as far as image acquisition goes. Also, when we are using these components, these oxy and deoxyhemoglobin, and then things like optical dyes, in this case we've got IR800, this is a dye that's made by Lycor, where we've already characterized this dye, and that curve, we've characterized it using the spectro feature, and we can load that curve into the software, and then we can choose it as one of the components for ease of acquisition of those images. So all we need to do is basically just tell the system what we're looking for. It will select all the appropriate imaging parameters. So really nice as far as the workflow, and also integrating some of the accessories, the hardware accessories that we've designed as well. We've designed a phantom, so for those of you who are doing a lot of contrast agent work, you want to characterize your contrast agent in a phantom in vitro before going in vivo. And we've designed this Vevo Phantom imaging dish across which we can string these tubes, and you inject your contrast agent into the tubes and do imaging. But now we've got, I don't actually have a screenshot of it here, but we've got an interface which allows really the easy acquisition and quantification of those contrast agents using this piece of hardware here. And also our Infusion Pump. So this is a pump we've been selling for a little while, but now we've actually integrated into our Vevo software the operation of that pump. So we can control the volume that it's going to inject, how fast it's going to inject, when it will inject. It'll also mark on the acquisition loop where you did the injection and the parameters of the injection as well. So we've gone to a lot of effort to really integrate some of these tools into the software of the system itself. I want to talk now about our new laser, and I didn't have a separate picture of it here. You can see it here, and you can already see that it's quite a bit more compact and more sleek. Really has a nice look to it, which matches the 3100. It's also faster, faster acquisition times. And it has an extended wavelength range, so I'm not sure, you can't see very clearly from the photo, but there are actually two separate ports here into which the optical fiber can be plugged, and I'll talk about the fibers in a second. And we have the standard range of 680 to 970 nanometers, which we have on our current Vevo Laser product. And we have an additional range here now that's available, the 1200 to 2000 nanometer range as well. You'll also notice that I didn't include a picture of the enclosure in this image here. When you're doing photoacoustic imaging, you're using a laser, and that laser light can potentially be harmful to the eyes, so we've designed an enclosure. And again, those of you familiar with the Vevo Laser will know this enclosure. It's a big box in which all of the imaging happens. We have our rail system, the animal platform, everything's in there. You close it up, and the laser won't fire if the doors are open. If you open the doors, it triggers the interlock and stops the laser from firing, so it keeps everybody safe who's using it in a shared environment, for example. But we also had a lot of requests to use this, for example, on larger animals like pigs, animals that won't fit inside the enclosure. So we've decided to have a configuration where an enclosure is not necessary. Of course, you've got to have the proper laser safety officers there and the proper protective equipment like safety goggles, but now this allows you to use it essentially as a handheld photoacoustic imaging device to scan larger animals like pigs, and possibly even doing some human studies under the proper ethical guidelines that have been established through an IRB, for example. Also, we've got more energy from the new system for improved sensitivity. This is one of the sort of biggest improvements that we've got here, and it comes from both the laser itself and the type of fiber we're using. So we're using a different type of fiber for this imaging, which gives us more energy. More energy translates into more signal. Better signal to noise ratio, we've got higher sensitivity. I want to talk now about the light delivery. We actually don't have a specific Vevo laser probe anymore. So we used to sell the LZ series probes, and that's for the 2100, the Vevo laser system, and they were completely separate from the MS series probes that work with the 2100. Now, you simply use your MX series probes that go with the 3100, except we've designed a jacket which is designed for each of those probes. So that jacket goes on the probes, and then we've actually separated the fibers themselves from the jacket as well. So yes, we've designed fibers which accommodate the full imaging width of each of these transducers, but let's say, for example, you're imaging something like the mouse brain. So you can't see it very clearly in here. It's a very, very tiny image. So this is actually a approximately properly scaled image of the mouse brain here, and I've blown it up over here at the side so you can see what that looks like. But as you can see, it's very small, and you might say, well, why don't you just use a higher frequency probe? Well, we want to get through the skull to be able to see at least some structure and have some sensitivity through the mouse skull. So let's use the MX201. This is a 15 megahertz probe. So I actually want to use this probe to see through the skull and get better sensitivity. But now I'm using a fiber that extends across the whole range. So essentially what I'm doing is I'm throwing away about 2/3 of the laser light. About 2/3 of the light isn't even getting into my target. And I'll still get an image. I might get an image of something like this. This is again that oxygen saturation parametric map image that you're seeing here with red being higher oxygen saturation. I might get an image like this, but now the big change that we've made is that these fibers are actually interchangeable with the different jackets. So for example, instead of having my wide fiber that's designed for the 201, I can actually take the narrow fiber from my MX400, and now I've got the light focused in. I'm not throwing any of it away. I've focused the light in all on my target, and as a result I get better signal. Well, I'm kind of proud of that animation. I'll show that again. So this is the signal sort of before, and now the signal after. We just get much better sensitivity, better depth, and since we're not even using the whole range of the transducer, this is a big advantage. I'm really excited about some of the possibilities for this because now the light delivery can be paired with the application instead of being stuck with using one particular transducer with one particular way of delivering the light.